everyone, today we will discuss Irodov problem 1.315, and before proceeding to the problem, let us first discuss the main concept behind that problem. Right, so what we have is we have a curved flow as shown here. These are the streamlines of that flow, and what here we have is the center of curvature. Right, so that flow is curving around this point. So what we have is, we know that if we have this small area, we consider a fluid element, basically this, and this area is A. Okay, because this is moving in a circular path, it will have a radius of curvature at this point. So there must be a force along the radius vector that is driving it, right? So what we want is that what is the increment in that pressure when we go by distance dr in this radial direction, because and we can say that here the pressure will be larger than this side because it must be experiencing an inward force. So let us do by Newton's laws, right? We have this center of curvature C, and we have these circular streamlines. So what I do is I consider a very small fluid element. Suppose this area is A, and this distance I consider R, and this increment as dr. Suppose the pressure at this side is P, I call it side 1 and call it side 2, and here the pressure is P plus dP, and the density of the fluid is rho. Okay, now apply the forces on this. There will be a pressure force here, that is PA, and a pressure force here, P plus dP times A. So the net force is along the radius vector in that direction, and that is equal to AdP, and that force must be equal to mv square by r. R is the radius of curvature at this point, the distance of it from the center of curvature, right? So that will be m, and the mass of this will be rho into its volume, that will be a dr. And suppose the velocity is v, that is mv square upon r. So from this what I get is a cancels out from both the sides. I get dp by dr, that is equal to rho v square upon r. That is a useful relation you will encounter in many problems. dp by dr equal to rho v square upon r, right? And the next what I have to do is, I have another one more. What can I do is, I can apply Bernoulli theorem between 1 and 2. Let us try what happens, right? Let us apply between 1 and 2. So what I get is, I get here on side 1 P plus half rho v square and rho gh, because this is a plane surface, this is a horizontal and smooth surface on which there is a steady flow. You have to take care of that, right? And before applying Bernoulli theorem, you have to take care that you are applying Bernoulli theorem on two different streamlines, this and this. You can apply Bernoulli theorem on two different streamlines only when the flow is irrotational, because only then that constant in the Bernoulli's theorem comes out to be same, right? And the flow is irrotational, and we can see that the curl, that is integral v vector dot ds vector, is 0. That basically we can comment, because we know the flow is irrotational. Like you can assume a sphere here, and that has a curl 0, that has no tendency to rotate about its axis. It has a tendency to move along the streamline. Yeah, we know that, right? So on this side 1 we have P plus half rho v square is equal to P plus dP, pressure on that side, plus I assume it to be V plus dV. Yeah, you think I took it V, but because there is an increment dr, I can assume these to be two different straight lines, and here I can take V plus dr. So half rho V plus dV ka square, right? So what now I have is, I want to find what happens, but what we get, I have half rho V square is equal to, as you can see, V plus dV squared here, right? So what I have is half rho V square is equal to dP plus half rho V square, I know cancel out, just write it, half rho into, I get 2V dV, and I neglect the dV square term. That would be very small, I have to do that approximation, and now from this relation I would get 0 is equal to dP plus rho V dV, right? So that is an important relation. Suppose I assume it to be 1 and take it to be 2. So what I can say is, from these two relations, send this, I have minus dP is equal to plus rho V dV, and from dP here, from the above, I can write minus rho V square upon R dV is equal to rho V dV. So I have V cancels out from this and rho cancels out. I have dV into V equal to minus, I think I have committed a mistake. Let me check. I have here 0 is equal to dP plus rho V dV, right? And I have minus dP equal to rho V dV. I think here I have dP is rho V square. Okay, here is dr, I am very sorry, this is dV, right? I had solved it earlier, so I know what happens. I have minus dV upon V then is equal to, there is a chaos there, okay, I will solve it for the sake of clarity. I write R like this, okay. So what I do is, if I integrate this expression, all of you could see now what happens. We get VR as a constant. Yeah, you can solve it easily. We get VR equal to constant. What does this mean? What does this basically mean? Right? What I have, I had a center of curvature C at this point. This equation VR equal to constant, some constant K. This equation tells me that as I go farther from the center of curvature, the velocity decreases. Velocity decreases means, how we represent this on streamlines? We say that the streamlines now have more gaps. They are more gapped. Like, okay, so in problem 1.315 of Irodov, right? We had the same problem. What we had is, we had a tube shaped this. You all can see the problem, and you can see in the description also, I have written the problem. We have this, and we have a fluid. This is the center of curvature C here, and we have a fluid flowing in this tube. So we have to draw streamlines. From this relation, VR equal to constant, I can easily draw the streamlines as I have told earlier. Now we can say that as the radius increases, velocity of the fluid decreases, any fluid element decreases, right? So the streamlines are gapped. So I can draw the streamlines like this. Initially they are closer, and then the gaps are there, right? This is sufficient. I think I can draw more, but then these streamlines would not be visible. right? What can I do is that I can assume the tube to be like this and they are gapped. Yeah, now you can say, right, this is a huge gap and this is a small gap comparison to this gap. As the radius r increases, distance from center increases, this v decreases, and this is a very useful relation that you will encounter in further many problems also, right? Okay,